Hey, how are you?
I'm good. How are you?
I'm good, thank you. Okay. So, yeah, good job on that test. And yeah, I got the document you sent me. So, let's see. Okay. What would you like to go over first?
Either one. I think maybe the
Mhm.
campus. There's a lot of orgo. Yeah.
Which one is that?
The one that doesn't say bio.
Okay, got it.
Yeah.
Okay, let's do it. Um, okay. So it's question 20, right?
Question 20.
Is that
Um,
or
it's two passages. Starts with like passage 4, and then there's
Mhm.
passage 7. Yeah.
Okay. All right. Okay, so let's see. You can, if you want, you can share your screen and then we can.
Let me see. Maybe it's best if I pull up the actual test and not the Word document. This isn't it, so I have to navigate to
Mhm.
it. This one, right? That's the first one that I have on the sheet, right? I think I didn't put in all the questions just because some of them I was very confident. But yeah, we can go through the passage first.
Yeah. So yeah, you can start off, but yeah, you could read it.
Yes. Chromoproteins are barrel-shaped monomers embedded with a chromophore, the pigmented prosthetic groups responsible for the colored appearance of the protein. I guess we've talked about like this like chromo, so like usually like resonance, like rings, benzene, things like this.
Conjugation, yeah.
Conjugation. Um Pigmented monomers. Okay, so there's like only one protein coming together.
Hmm.
Has a chromophore, so it has the pigmented prosthetic groups responsible for color appearance of the protein. Okay. CP chromophores and fluorophores of the related family of fluorescent GFP-like proteins contain the amino acid sequence X, tyrosine, and glycine. And here they bring up fluorophores, so like fluorescence. So I think we talked about fluorescence, have we?
Hmm.
Um, yeah, we talked about like electrons, like electrons moving and losing energy. Yeah.
Yeah, so for fluorescence, right? Tell me a little bit more about that. Like, what do you typically see happen?
Um, you're going from a higher energy state to a lower energy state.
Hmm.
Um, so you emit photons
Yep.
in the
So
process.
yeah, so it's like when you have, let's say, n is equal to 1, n is equal to 2, n is equal to 3, and let's say you have let's say you have like a photon that has the energy that can be absorbed and has energy that will be enough to, let's say, excite an electron to the n is equal to 3 shell. Um, and typically you would see like it go back down to n is equal to 1, and it'll emit a photon that's of the same energy as the photon that gets absorbed. But with fluorescence, due to the nature of the molecule's stability caused by resonance, you will see that the molecule will enable an electron to kind of relax down to, let's say, the n is equal to 2 shell. But it does this without the emission of a photon. It does this through like intermolecular interactions, aka the resonance stability stuff. So it will enable an electron to relax down to a lower energy shell without the emission of a photon. And then from there, when it goes back to its ground state, that's when it'll emit a photon. But the photon that's emitted is just the energy difference between the first and the second shell, which is less than the energy difference between the first and the third shell. So with fluorescence, you would have the energy of the photon absorbed will be larger than the energy of the photon emitted.
Mm.
Which would also mean that the wavelength of the photon that's absorbed will be less than the wavelength of the photon emitted. Right? So, okay, cool.
Yes.
Mhm.
Okay, so they contain that amino acid sequence. CP chromophores form an imidazolinone structure through autocyclization and dehydration reactions shown in steps 1 and 2 of figure 1. The active green fluorescent CP fluorophore, GFP, is formed by a final oxidation step.
Mhm.
So they're describing here.
Yep, so we see here that, what's happening in step 1 here?
So this carbonyl it's getting reduced into just an alcohol group.
Okay. Um, um, Anything else? Like from the passage, right? They tell us kind of like what happens in steps 1 and 2.
Okay, so there's dehydration, there's autocyclization,
What do you think that would do?
like forming a ring, that's what I'm thinking.
Mm-hmm. And do we?
But I don't see a ring forming.
Are you sure?
Yeah. Sorry?
Are you sure?
Maybe step 2.
No.
Sorry.
Step 1.
Step 1.
This.
What in the world? I see.
Mm-hmm.
Yeah.
Yep.
Okay. It's hard to tell.
Yeah.
Yeah.
So yeah. So okay. So that means that yes, that a ring that's the autocyclization step, right? Because yeah, I know that, goes from the carbonyl to a hydroxyl group, but why, right? So, you know, um, well, the nitrogen can have a lone pair, right? And that can act as a nucleophile, right? And it can nucleophilically attack that,
Hmm, I see.
which would,
Opens it up.
yep. And then you'd get a bond between this nitrogen here and this carbon here, which would mean that the double bond, the carbonyl carbon here, can no longer have that double bond. So, you know, so when it binds to this will go up here. So you'd have that O minus bond, and then it picks up like a proton.
Okay, I get it. I see it now.
Mhm.
Um, yeah. And then there's the dehydration.
Uh-huh.
And let me see. Yeah, we no longer have that OH group.
Hmm.
That's it.
Yep. So it seems like, this OH group leaves, and like the electrons here can form a double bond here, like right there.
Yes.
Hmm. Cool.
Mm.
Because like when you have dehydration, you typically have synthesis, right?
Yep.
Cool. So good. So yeah, we have that um, double bond now in that imidazolinone thing. Um, okay, cool.
Yeah.
Mhm.
So this should be a final oxidation step.
Mhm.
Um, okay. So yeah, so I see the reduction of the oxygen, I guess, is coupled to
Mhm.
this oxidation here.
Yeah, I think this would be the oxidation step here, the step 3.
Yeah. Like like this becoming, oh, it's not this becoming this.
Oh yeah, yeah, it'll be like that, forming, you know, one of these over here.
Yeah.
So that's the oxidation step, and it seems like what's happening is, well, we get this double bond there, right?
Yes. Ah, it's so difficult to see these things.
Yeah, yeah,
Yes.
that's true. Okay, cool. So we see that that gets formed, and then we just have like, so I would like look at this thing up top first, I guess. And if it then loses a proton, it'll give you the thing on the bottom. And if the thing on the bottom gains a proton, yep.
Yep.
So if we get rid of that, we get the thing on the bottom. And then if we add it, we get the thing on the top. Right?
Yeah.
Okay. So yeah, that's figure 1, mechanism of the post-translational autocyclization of the, I was just reading the caption.
Oh.
Mhm. Of the jellyfish green fluorescent protein chromophore.
Yep.
Yeah, and we can also kind of see the amino acids that were mentioned, right?
Yeah. Yeah. Tyrosine.
Uh-huh. And
Sometimes when I have these, I have difficulty tracking them.
yeah, yeah, yeah.
This,
I would start from the first thing that we see here.
here. Okay.
Because that's what they mentioned, right? Uh like up top. I think they
Mm-hmm.
mentioned like yeah, the um X tyrosine glycine. So we have our tyrosine there, right?
Yeah.
And what else do we have here? There should be a glycine somewhere, right?
Yeah.
Could be that one, right? Because we wouldn't draw like the
Like
H.
this one?
Mhm. Yeah,
Yeah.
there would be like an H here, right?
Yeah.
So yeah, that could be the glycine, and then the X would be something else. And from this, it seems like that's like some type of either like threonine or serine or something like that.
Yep. They have a question that's on that. Actually, I mean, I can here.
Mhm. Yep. So we know that, well, what can we eliminate, I guess?
Glutamine and glycine.
Yep. And so now I guess we just have to try to think about what's the difference between serine and threonine.
Yeah. I think threonine has a methyl group.
Mm-hmm.
Um, yeah, but still, like I am having trouble locating exactly the side chain here.
Mm-hmm.
So this is the
You can see like the amide bonds, right? Like there's one here,
yeah.
there's one here. So the amide bonds can help you because those would be where the peptide bonds are. And the one that would be next, like the next carbon over, would be that um where that like initial like where essentially where the R group would be attached to. So like this one has this R group, which is for the tyrosine.
Oh, I didn't realize that. Okay, so like this is good. So I identify the like amide.
Mhm,
Um and so the next carbon over should be my R group.
mhm. Or it should be the carbon that's attached to the R group.
Okay. Okay, so like this. Okay. So here this is this it's just one OH, so it should be serine.
So so we see that this amide here is the peptide bond for this one. So the next one over should be here, right?
Where's your cursor?
Oh, here.
Yeah.
Mhm.
Yeah, so I would go with serine, just because if that's the side chain.
So it seems like there's that extra methyl group here.
Isn't isn't that serine?
Let me make sure, because I think serine, I think threonine is like serine, but with that extra methyl. Let me make sure though.
I thought it was in a different position, like not in a straight chain, the extra methyl.
So serine. Oh, so okay. Serine is just going to be like the met that extra methyl and then the OH, and then threonine is like an extra methyl, but the OH
Yeah,
is bound to that first one.
yeah. Arcturian is like a tree. Yeah.
So this one, the extra methyl, the OH group seems to be bound to that extra methyl, right? Like here.
Yeah.
So yeah, I think you're right with it being serine.
Yeah. Yes. I guess we can keep reading the passage, right? The imidazolinone structure, together with the tyrosine group, form a conjugated system of pi electrons that cause excitation and emission in CP and GFP-like proteins. Okay. Crystal structure analysis reveals that C-anemone CPs contain the tripeptide QYG chromophore, glutamine, tyrosine, glycine, located at the central axis of the barrel. When both the phenyl side chain of Y63 and the hydroxyl group on S157 in SGBP are protonated, hydrogen bonding occurs. The strength of this bonding is important in excited state proton transfer, which determines the chromophore absorption spectrum. Okay. Okay, there's sort of okay. Describing the structure of the barrel. So I guess this is referring to like the shape, the three-dimensional shape. I'm not sure what they mean by the barrel.
I think it's just what they mentioned in that first paragraph where they talked about the chromoproteins. They're these barrel-shaped monomers that are embedded with the chromophore, which is the pigmented prosthetic group.
Okay.
Yeah, and then they have I think the thing that they're talking about with the protonated thing is something we can see like here. Like I think
Like the phenol and the
yeah, wait, this is weird. This
hydroxyl.
didn't have anything here, right?
Sorry?
That there's nothing there, right?
No.
That's weird. Okay, so I guess this one, it's a little weird, but okay, whatever. So, you know, the OH group goes there. Okay. Okay. So yeah, I guess if they're saying the phenyl, when you have the tyrosine protonated as well as the serine or the hydroxyl group there, hydrogen bonding can occur.
Okay. I guess, is it referring to this molecule?
I think it's talking about a new one. That falls in like to be like the one that they showed us here is like the X thing where we don't know what that X protein or amino acid could be. But you'll also have the tyrosine and the serine. And then for this one that they're talking about for the sea anemones, there's they're saying that when the tyrosine is protonated and the serine is protonated, there could be hydrogen bonding that can happen.
Okay.
And the strength of this bonding plays a role in this type of chromophore absorption spectrum of like, I guess, photons that it can absorb.
Okay. Experiment 1. Several mutations of SGBP were generated to assess changes to its chromophoric proteins. Optical properties of the mutant proteins are shown in Table 1. Summary mutation sites on the protein, where the wavelength math is the wavelength of maximum light absorption. Epsilon is the molar absorptivity of the protein. So you have the mutations, wild type first line, first row. The mutated residue, the max wavelength, which is no, I don't know. Wavelength maximum absorption. The epsilon. What is this? Molar absorptivity of the protein and the appearance. Okay.
It's like when you had like the Beer's law with that kind of thing, where C is like the concentration, whoops,
Yeah.
and
Path length
yep,
and
yep,
yeah.
that kind of thing. So okay, let's see. So the wild type, no mutated residue, 608 nanometers max wavelength. Um, the molar absorptivity, and then the appearance is blue. And then we have we're modifying the glycine 62 residue and we're turning it into serine 62, like the 62 because it's in the same location, right? So, this type of thing. They're just taking the glycine, or wait,
Glutamine, I think.
yeah, because of the Q. So yeah, I got it. So the glutamine at the 60-second position is turned into a serine, and we don't have a value for the wavelength of max absorption. And we don't have the molar absorptivity either, but we do have the appearance, which is colorless. So maybe that's why we don't have like um a wavelength of maximum light absorption or the molar absorptivity because it is colorless, right?
Yep. Yeah, and I guess that's the same for all of these that are colorless.
Mm-hmm. And then we have the next one, we're replacing it with a methionine, and pretty much nothing changes, right? We still have the same max wavelength, the same molar absorptivity, the same appearance of blue. And then we have when we turn the um glutamine, no, the glutamic acid to aspartic acid, we get something that's colorless again. And if we turn the serine into threonine, we have a change in the the wavelength of maximum light absorption. It goes up. So if it goes up, the energy of the photon that it absorbs, right, goes down. And the molar absorptivity seems to go down. And we have light blue. So, okay. Um, so, okay. And then we have the same type of thing, except for turning the serine into a cysteine. And this time, so it seems like the 608 wavelength or whatever, let's kind of so like if we have 604, which is below it, and 611, I mean we're also changing the molar absorptivity, um but it seems like if we get some value that is below this, the 608 is the blue, the value below it seems to be a dark blue, and if it's above it seems to be like a light blue.
Yeah.
So there's also the change in molar absorptivity, so I can't say anything definite about like a relationship between um the lambda max and the color, but that's just something that I see that's different, that might be a little consistent. Um and then the last thing, colorless again. Okay,
Yeah.
cool.
Okay.
Mhm.
To assess how pH influence the optical properties of wild type SGBP, S157T, and S157C, these mutations, and the colored ones, the ones that produce that we have the information for. Their absorbance spectra were measured under different pH conditions. Okay, normalized absorbance and wavelength. And these are the different mutations. And this is the wild type SGBP, I think.
I think everything there is. Oh, it's a little confusing because they have a capital S for the mutation and then a lowercase s for the not mutation.
Is it? Wait, is this also a not mutation?
Oh, like when I say I mean like it's not a mutation.
Mm, isn't S157C also a mutation, or is that?
I think the lowercase s.
I thought this wasn't a mutation. This was the wild type SGBP.
Um, yeah, I think the so both of these are not mutations, right?
Oops. Yeah.
Just because the lowercase s doesn't mean serine, right? But this is the mutation.
Right, but here it's uppercase.
Yeah. So the
And here it's
uppercase
also.
one, yeah, the uppercase ones are the mutations,
Okay.
right? Because uppercase and then the location and then uppercase again. So this is serine.
Are you sure that second one isn't the typo? Because it still has it's this one, right? S157C.
That's sort of there. I mean, yeah, I guess it. Yeah, I guess.
Two different pHs.
So. Let's see. So S157C at a pH of 10. Yeah, I guess it's a typo then. That's pretty annoying. Um, okay, so if we treat that as a typo, then that would just be the same thing, but at a pH that's higher, and then we just have SGBP, which isn't a mutation. That's the wild type. Um, yeah, I guess because they mentioned over here, we only get the wild type SGBP and then this mutation and then this mutation. So yeah, I guess it's a typo.
Yeah.
So okay, so it seems like when we have the S157C, that the absorbance, the wavelength of maximum absorbance does not change, but if the pH goes up, it seems like the absorbance goes down.
Yeah.
Okay. And then we have, yeah, the wild
Is
type.
wait, do you repeat? So from 11.5 S157C. So yeah, so we have three different values for S157C. So it's weird because it's not going in a normal linear direction,
Mhm.
right? So when it's 4.5, it's still lower than 11.5.
Mhm.
But 10 is above all of those. So I guess it has like an optimal range that's probably between like 11 and 10 or 11 and 9. I don't know, 9 to 11.
Mhm.
Yeah. But for wild type, higher is better, right? Yes. Yeah. So under the results shown in using the results shown in figure 2, a mechanism, figure 3, was proposed for the protonation state-dependent ionic interaction of Y63 of wild type SGBP and S157C chromophores at pH 11.6 and pH 10, respectively. This mechanism accounts for the greater strength of ionic bonds relative to hydrogen bonds. I'm so confused. Yeah, like with the passage, because there's so much information.
Yeah. So I guess like prior to this, like if you go up a little bit more, um, yeah, even above that. So we're being told um that when these things are protonated, hydrogen bonding occurs, and that the strength of the hydrogen bonding that happens um affects like the absorption spectrum. So we have that. absorption spectrum like below table 1?
Yes.
And we can see that. I think it would be good
I
to.
see, like protonation effects or absorption spectra, so varying pH or varying the protonation state.
Yeah, so I think it would be easy to think of it as like pH above 7 gives you like, I guess, these types of values that would have essentially the same, because the pH is going to determine what gets protonated, what doesn't get protonated and stuff. And they say that that affects the absorption spectra. So we get to see here that pH, maybe above 7 or whatever, basic environment, right? We basically have the wavelength of maximum absorption is pretty much unchanged, but we do see that the absorbance goes down. And then when we have pH is lower than 7, like 3.4 and 3.5, we see that the wavelength of maximum absorption, changes, because it's no longer like, the normalized absorption is no longer like maximum at this wavelength.
Yeah.
So it seems like, at the higher pHs, that wavelength of maximum absorption doesn't change much, but the absorption, like I guess, absorbance changes. And at the lower pHs, we have change in both absorbance and wavelength of maximum absorption.
Yeah.
And then we have this like one with like the pH of 4.5, which is also different. Different in terms of both the absorbance and the wavelength of maximum absorbance. Yeah. Then, yep.
Okay, so they created this mechanism for, yeah, how pH changes is affecting the interaction. Okay, so we have QYG. Bonding of the QYG chromophore. First part, we have Y63 anionic phenolate group with wild type SGBP at pH 11.6. And then in B, we have Y63 phenolic hydroxyl group with deprotonated S157C at pH 10.
Yeah, let's see. So the caption says bonding of the QYG chromophore. For A, it's the Y63, the whatever, the tyrosine is anionic. Anionic phenolate. So this thing over here.
Yeah.
And it binds with the wild type SGBP S157 at pH 11.6. So it's a little weird, but I think they mean like this here is at a pH of 11.6. The reason I say that is because there's nothing listed here, but here, they have, the cysteines, pKa. Right. So for B, it's the QYG is at the same pKa, or wait a sec. Okay, pKa different from pH. So I think that they're just telling us that the pKa of the tyrosine of the Y63 is 10.46. And they're telling us, they tell us here as well, this is that, let's see. Wild type chromophores at pH. So I guess, yeah, I guess L, this entire thing is a pH of 11.6, and this entire thing is a pH of 10. So the pKa's can then help us navigate that, because the pKa of like the tyrosine seems to be, it's 10.46. And then the pKa of the cysteine,
I guess that explains why it's deprotonated and this is proteinated.
yeah. Oh, and then this is a serine here, but it's a cysteine here. So I guess the pKa of the cysteine is 8.37. I don't know if they tell us what the pKa of the serine is, but it seems like when they have the cysteine, or rather, so okay, let's think about it like this. So 10.46 is the pKa of the tyrosine. So if the pH is larger than the pKa, would that result in protonation or deprotonation?
Deprotonation?
Yeah, because the um, pH of the environment is larger than the pK of the molecule. So the molecule is in a basic environment. So that should cause the proton to be removed. And so we see that here, pH larger than pKa, deprotonation, right? And then here, pH is less than the pKa, so it doesn't get deprotonated, so it's still there.
Yeah.
And then let's see. Okay, so let's see. So the serine can hydrogen bond. Well, I guess it's technically ionic interaction because of this negative charge here. But that's the ionic interaction between these two, between the QIG chromophore and the serine molecule. And then on the right, we have that same QIG when it's protonated, but this time so I guess the wild type is what keeps the, like this, I think this is the wild type, right? Yeah, it must be, because the mutation would change the serine into the cysteine, right?
Yes.
So this would be like the wild type with the serine here. And then this is the mutant with the cysteine at the 150, the serine at the 157 position turning into cysteine.
Yeah.
And then the cysteine's pKa is 8.37.
It's a really weird way of doing this because they're doing two changes at the same time, like
Uh-huh.
proposing a mechanism because they're changing the pH and they're also changing they're having the mutation instead of doing it one at a time.
Yeah, yeah. So I think what we can take away from this is just that um well, we can I guess see that um how should I put this? So a mechanism was proposed for the wild type thing at the pH of 11.6, and then the mutation, the mutated one, at a pH of 10. And yeah, they're changing both. So that's kind of annoying, but I think the main thing we're trying to, or that we want to obtain from this is just that, like that this mechanism that they're proposing is, or should account for, the greater strength of ionic bonds relative to hydrogen bonds. Because what we see here are ionic bonds, right? And So like this should tell us that the ionic bonds are stronger than hydrogen bonds. So I think that's kind of all we need to really take away from this. Because like, if you had here, if you had the pH of 10, right, you would likely get this here, and that would be a hydrogen bond with the serine.
Yeah.
And then here, you would probably need like the pH to be like, lower than this to keep a hydrogen there. So that would be also like a hydrogen bond. Well, maybe not actually, because the serine attached to the H wouldn't be a hydrogen bond. So I think that could help us. But all in all, this is very hard to kind of like understand. So we don't need to understand every single aspect of this. We need to understand what we need to understand to like answer the questions. So we can just see that ionic bonds like versus hydrogen bonds is going to be something that plays a role here.
Yep.
So yeah. So okay. So we get to see certain things. But for the most part, yeah, it's kind of hard to navigate all this, but you just need to, I guess, take away like I guess think about it as like what's the minimum or what's like the minimum amount of stuff that I need to understand here for me to answer the questions. Because like that's also like what you'll see in these blueprint tests. Like it's just going to be things that look hard, that are hard, but they mostly look hard. So I always say that you don't need to understand every little aspect of everything that they show you. You just need to understand enough to be able to answer the questions. So like this question 20, we were able to answer like before we even looked at the choices, we knew that it was going to be like sarin or threonine or something like that. Which is kind of annoying because usually we think like, okay, sarin, threonine, tyrosine, they have hydroxyl groups, and tyrosine is the one with the phenol, the benzene. So usually we can differentiate between the tyrosine and then the sarin and threonine, but usually we kind of lump the sarin and threonine together. So, they're actually asking us to make to be able to know the difference.
Yeah.
And you were able to do that. So good job with that.
I want to go.
Yep.
And I also, well, I've done this before, so I also, what you did was like spot on, like this is sort of what I was doing in my head when I was completing this. And it's like the wavelength is the, like what's, the answer to this. Remember it was increase or decrease, but it would S157. S157.
Yeah. We see that so we see that the lambda max changes. We also see that the epsilon changes. How do we know which one matters?
The other one is random.
The
It's
other
like not following a pattern.
Oh yeah, right? Because if we think about the blue as being in between dark blue and light blue, then the max wavelengths follow that type of pattern with 604 being less, 611 being above, whereas the epsilon value is lower for both of these. So it's not like this value is in between this and this.
Yeah.
So yeah, sometimes we just need to do the best we can do.
Yes. Okay. So the first step of the formation of the imidazolinoone ring up SGBP is most likely accomplished by the. Could you erase this? Is that possible? So this, oh, I mean, we went through it. The nitrogen nucleophilically attacks the carbonyl carbon. Okay. So we know it's attack of an amide, but let's see which one. Is it necessary? Yes, it is. Glycine 64 or 62? What? Glycine 64 or 62? Like the position of the 64 or 62? Does this tell us if it's like 64 or 62?
Mhm. Um, let's see if we need that, right? Because remember when I first asked you, like, if you look at the amide, you would know that that's where the peptide bond is,
Yeah.
right? So we know that we have like a tyrosine here. We know that we have a glycine here, but that's like a something else, right? Like a serine or something. No, wait. So okay. Oh, sorry. So yeah, it could either be the glycine attacking um some.
Oh, I see. I didn't even see that difference when I was reading this. I thought it was just a
Yeah,
number difference.
they look the same, yeah.
Yeah.
I was
Yeah.
just like yeah, as you were saying, like how do we know like the difference between 64 and 62, right? But
Yeah.
we know that at least we know that so we know that it's not going to be anything with the tyrosine.
It's not glycine attacking, so yeah.
Which nitrogen is acting as a nucleophile?
This one?
That's the one attached to the glycine, right?
It's yeah, you're right.
So we should see glycine being the nucleophile, right?
Yes.
Mm-hmm. So maybe the first time you didn't see the ring part, the ring autocyclization thing.
Yeah.
So, but um, but yeah, I would say that yeah, it looks like a mess, you know? I'm not gonna lie. But um you want to do the best that you can do. So if you see the amides, you can see that those will be the peptide bonds. So between each amide will be the actual amino acid.
Yeah. Let me make sure I get that. Okay, so like here, let's take this molecule.
I'll just put this for the amides.
Yeah. Um, the carbon, so it's usually like of course like a carboxyl group, like the carboxylic acid and the amide. So you have the bond. So that's how you're identifying each unique amino acid, and that's how you know that there's three here. Let me make sure I get that. So this and this one.
Mm-hmm.
And then this, wait, yeah. Here in the bottom.
That's a good idea. I forgot you could do.
Yeah. So I guess this would be another one. It's just not shown.
Mm-hmm.
Um, this is one. This one. Okay.
So,
Okay.
so what I would do is, so for this one,
Oops, I should stop moving this. I'll just there.
so yeah, for this one here, I would just see, okay, that's the amide, so that's the peptide bond. So to the left of it will be one type of amino acid. To the right of it will be another type of amino acid. Then I see a peptide bond here. So that means that on this side will be our third amino acid. So we see that there's a tyrosine here. We see that there's nothing here, which means that it would be the glycine because that would be a hydrogen, right? So a glycine, a tyrosine, and then this is the one where we were like, it could be a serine or a threonine. I think it ended up being a serine.
Yeah.
But yeah, I would say to look for the amide bonds because those will be the peptide bonds, and then what's on one side will be one amino acid, what's on the other side will be the other amino acid.
Yeah. Okay.
Mhm.
I'm gonna zoom out now. Okay, this makes sense now. Okay, it is found that in the absence of molecular oxygen, the resulting imidazolinone containing reactant is not fluorescent. According to figure 1, what best explains the inability to fluoresce? A, the 5-membered ring is not conjugated at the aromatic phenol ring of tyrosine. B, the tyrosine side chain is a final chromophore remains deprotonated. C, the reactant lacks conjugation among any double bonds. D, the more thermodynamic. Okay, so I know it's between A or C because I know it has to be with conjugation for fluorescence. Yeah. 5. So absence of molecular oxygen. Not fluorescent. So I guess they're referring to this final compound.
Mhm.
What is what's its ability to fluoresce?
Tell me the how you get to that from the previous molecule.
How I get to from here to here. So oxygen is being reduced, so this must be oxidized. I see.
So yeah,
I see.
they're asking us, so if we have molecular oxygen, right,
Yeah.
what changes from this to this?
Oh, I see. Um, so I don't have that double bond here.
Mhm.
I guess that's the imidazolinoone
I
thing group they mentioned, maybe.
think
Uh,
it's this
uh
thing.
yeah,
But yeah, so the molecular oxygen lets there be this double bond here, right?
yeah,
So there's conjugation between the 5-membered ring here and the tyrosine, right?
yeah.
If you don't have that, you won't have that there, right?
I see.
It'll just look like that.
Yeah.
I
Okay, that makes sense. So it's A for sure.
think so. 5-membered ring is not yeah, wait, not conjugated with the aromatic phenol ring. Yep.
Yeah.
Mhm.
Okay. Alpha max of S1, wavelength max of S157C at pH 4.5 is greater than at pH 10. How does the proposed bonding of deprotonated this thing with Y63 at pH 10 account for this observation? S1.5 pH 10. Okay, I guess wavelength max is different from absorbance max. Yeah, probably. It appears. pH 10. Compared to the hydrogen bonding at pH 4.5. So, no, that's not 4.5. Ah, right, they're not showing us a 4.5. The ion dipole interaction at pH 10 destabilizes the SGBP barrel formation. Decreases the maximum normalized absorbance.
So if the wavelength max increases, what does that say about the energy?
On the passage.
Just in general.
Usually it's more energy. Wait, wavelength max, less energy emitted.
Yep.
Mhm.
So if they're saying that the lambda max is greater for this thing at pH 4.5 than at pH of 10, that must mean that, and they told us that that was dependent on like the ionic interaction thing and relative to the hydrogen bond, right? And they said that the strength of the ionic bond is more than the hydrogen bond, right?
Yes.
So the lambda max should be smaller for something with a larger strength, right? So
Yeah.
ionic bonds should be the one that produces a smaller lambda max, because we know that ionic bonds are stronger from what they tell us.
Yes. Yes.
So yeah. So we want to see something that will essentially state that we have weaker bonds, which are likely going to be hydrogen bonding, right?
I guess the thing is, how did you get to thinking about like the energy of the wavelength max? Because like I guess I would think of that when it's like emission, like spectroscopy, but this is absorbance.
Mm-hmm.
Yeah.
Let's see. I think I was just thinking about the figure 2. So yeah, this thing. And so at pH 4.5, the max seems to be like either here or here, right?
Mhm.
And it's at a higher wavelength compared to here, right?
Yeah.
So so yeah, if it's a higher wavelength, I just associate that with um a lower energy. I guess I didn't differentiate between the energy of what's absorbed and the energy of what's emitted. Um, but I think it could still work. Let's see. So, and I also know that according to what they said, that the ionic bonds would be stronger. So I would be looking for something that would, if it's a higher lambda max, I think I would just associate that with a lower energy bond like hydrogen bonding, and then compare that to pH 10, where it's a smaller lambda max, which I guess I would associate with a higher energy. So um so yeah, if we look at this, they're saying compared to hydrogen bonding at 4.5, I think we should look for something, an ion dipole interaction that would there are different things that they're saying. So let's see. Um, so A says ion dipole interaction at pH of 10 destabilizes this barrel formation or whatever. Okay, that's destabilizing it. So, okay, then they tell us after that ion dipole interaction decreases maximum normalized absorbance. That's just absorbance. But I think I want to look for something that talks about energy. That I see ion dipole interaction at pH 10 promotes peak absorbance of higher energy radiation. That would be in line with what I would be looking for, because we know that. So we know two things. We know that we know that this produces a higher lambda
Yeah.
max, which means a lower energy. So that this is at least talking about things that I am thinking about. And
Yeah,
then
and just reading the graph, I mean, that is a true statement for
Mhm.
now. Like at 4.5, if we look at this, it is at higher, it's at higher wavelengths, the absorbance.
Mhm.
And at 10, it's at lower, so it's higher energy.
Yeah, and I think with they want us to connect that to what they said about the greater strength of ionic bonds. So if we see something with a higher lambda max, we should see something that would have more perhaps hydrogen bonding. And then all the things start with compared to hydrogen bonding at pH of 4.5, right?
Yeah.
So we know that at pH of 4.5, we have weaker bonds, which would be aligned with a larger lambda max.
Yeah.
So, so I think it would be like either C or D then. And then let's see, ion dipole interaction at pH 10 promotes peak absorbance of higher energy radiation. That is what we're looking for, I think. And then this one says ion dipole interaction at pH 10 increases the wavelength. If it increases the wavelength of
It
max,
decreases.
it decreases the energy, I think.
So
Yep.
these are opposites as well.
Mhm.
See.
So yeah, I think that would be C.
Yeah, I think it would be C too. Very convoluted, and I think it would be C.
Yeah. So like, yeah, don't like I guess the main lesson here is to understand that they're going to give you passages like this to psych you out. And pre-meds in general, we want to like understand everything. So we can get easily caught up in the details here, but you're only required to understand like think about it, I guess like yeah, you just want to be able to answer the questions at the end of the day. So to understand what you need to understand to answer the questions, I would say. So when we first started reading this, they mentioned that um, that autocyclization happens in step 1, dehydration in step 2, right? And then a final oxidation step. So here, I think you notice that where this carbonyl turns into a hydroxyl, but you want to think about what they told you, which is autocyclization. So you want to look for that. I think like if you were looking for it, you definitely would have seen it, right? And then here it's a dehydration step. So we're going to look for that here. And then here is the oxidation step with the oxygen.
Yeah.
And then from there, you can see there's some stuff happening here. But just kind of like see if you can get like the minimum. I'm trying to think of like if to use maximum or minimum, like the minimum amount of information or the minimum amount of like understanding of the passage to answer the questions. So yeah.
Right. I guess so. Based on results presented in the passage, researchers hoping to alter their appearance of SGBP while maintaining its function as a CP providing a colored appearance would most logically choose to mutate with which SGBP residue. then analyzing this chart, I guess. Maintaining the function. Yeah.
So it says
So
maintaining.
definitely none of the colorless for sure.
Yeah.
If
Yeah.
there's any of that, yeah. So like A would be out. It's the only one that would be out. Is this even here? Yeah, it's also colorless. It would be out. So, or, oh, this is also colorless. Right? Yeah, blue 144. Yeah, so I would say C just because it's the only one that's colored.
When you mutate it, right?
Yeah,
Mhm.
not bad.
Mhm.
Just a very, very like scary passage.
Yep.
But yeah.
That's exactly what it is. Yeah. But yeah, you are like like in addition to just these tests being harder, um, what you also learn is like psychologically speaking, like how to deal with really hard looking passages. Um, and you just want to do the best that you can do.
Yeah.
So yeah. All right, cool. So we can do the rest tomorrow, right?
Yeah, I think I'm exhausted
Yeah,
from
yeah, yeah.
the
I
whole
can't
day.
imagine. Yeah,
Yeah.
that's tough. Okay, awesome. Yeah, but you're still doing a great job. Okay.
Yeah, I am a bit worried because like my test date is approaching.
Mhm.
Yeah.
Yeah, maybe like by the end of this week we can decide because either you'll be taking another blueprint and then AMC, or we can start the AMC like 1 week early. So I think the AMC one will like kind of like help you feel a little better.
Yeah.
Blueprint
Not
tests are
feeling
really
great right now.
crazy.
I feel like
Yeah. Yeah, yeah.
scoring the same or lower.
Yeah, yeah, which is fine for blueprint. Like you're not going to really see like linear growth or anything like that, but if you're just able to maintain some range, you're doing good. And also like every test you take, like even if you don't see your score increase, like you still learn every single time from, stuff that just may not be tested again for like a couple of practice tests. So it may not feel that way, but like regardless of your scores, like you're learning every step of the way.
Sounds good. Yeah.
Yeah. And yeah, it's a long, you're doing this like after work and all that stuff. So it's a lot. It's a lot. If you want to like, yeah. So if you ever want to like take a day off or anything like that, just let me know.
Okay.
You're doing great.
Sounds good.
Yep.
Thank you.
All right. Take care.
Bye.